Okay, I can see we're live now. So good morning everyone and welcome to today's session. I'm Mithuna Murugesh, the RIBA Business Development Manager for the Gulf, and it's my pleasure to be hosting Module 5 of the RIBA and Geberit seminar series, which have actually been reinstated for 2021 due to popular demand. So let's jump straight into today's session. We have a very exciting and interactive session. Today's module of the RIB and Geberit seminar series will provide an insight on designing drainage without compromise. We will be following the same format as always, so please send any questions regarding today's presentation in the chat bar alongside at any point of time, and our speaker will attend to them in the last 15 minutes Q&A session. So to begin, I'd like to introduce you all to Louise Pitt, the Marketing and CRM Manager at Geberit. Over to you, Louise.
So good morning, everybody. And also we'd like to extend a very warm welcome from us here at Geberit. Today, we're very happy to be transmitting live from our regional headquarters in Dubai Design District. So today I'd like to introduce you to our speaker, Mr. Remo Hirschi. Remo is a 39-year-old Swiss national, and we've been lucky to have him working in our international markets for the last 7 years. Remo has a Bachelor of Science in Engineering, and today he's very happy to share with you his know-how on designing drainage. Over to you, Remo, where he will now do a quick demonstration of our live module here in Dubai Design District before going into the presentation. And then we're all looking very forward to a very interactive question and answer session at the end. Thank you.
Thank you very much, everybody, for the introduction and for this great opportunity. So as mentioned, my name is Remo. I will be the speaker for the next couple of minutes, and we're going through designing drainage without compromise. And so we're going to kick this off with a live demonstration here with our hydraulic module. And just really briefly, what we are seeing is here in the front, a 110 or a 4-inch pipe with the special fitting, which is basically used on each floor to connect the bathroom layout. So this will be the horizontal connection, let's say, on each floor. And then we have the stack, and then it's transferred, let's say, if we think on a hotel project, for example, on the lobby level, where we have a deviation into horizontal, and then it continues back. On the backside, we see basically the same. It's a 160 millimeter pipe with a parallel ventilation. So it's just two different type of systems what we are seeing here, but both have the same capacity. So we talk always about capacity and how many liters per second you can drain with your drainage system, depending on the number of floors and the number of fixtures you're having in your bathroom. So these two systems come more or less with the same capacity, which is around 12 liters per second. But of course, you can see here the difference. One is just a 4-inch pipe, and the other one is a 6-inch plus a parallel ventilation. So I'm quickly going to start and give it some water through the pipes. So we have some pumps here installed. It's pumping the water up, and then it comes down and simulates basically how this looks. And of course it's transparent, so we can see the water flow. So we see here water coming down, then it's guided around the 90-degree angle with two 45-degree bends. And why do we require a secondary ventilation? I'm not sure if it's really clearly visible, but what happens here, through the impact of the water here on this area, here we create, or the water is creating a jump, and this creates some overpressure. So overpressure would mean that the air is getting squeezed and needs to go somewhere else. So it expands, and then it would probably, if we would imagine we would have a connection here one level up, the water could spit out of the WC, for example, which would be worse. So how to guide the air in this case? We have an additional ventilation pipe, which is connected then as well to the same system. So it's like a bypass for the air to circulate. So to drain this amount of water, we require the size of the pipe plus an additional ventilation. Now the small pipe with the same amount of water, as you can see, how this works. So we see again, water is coming from the stack and then it's converted into horizontal, but we have some special fittings which have been engineered by our specialists, and they create the transition here much smoother. So from an annular flow, what we call it here in the stack. So we see the water is rotating and the air column is always going through the stack. Then here it's converted into horizontal, into a layered flow. So it means straight away it's straight, and we can see that the air can circulate throughout the entire system. And the same happens then when we convert back. So straight away the layered water here is then set into rotation again, and in the center you will see here now enough space for air to circulate throughout this construction. And yeah, I think now the next minutes we're going to elaborate with the PowerPoint presentation a bit the basics of hydraulics. Why do we require air? Why here we require this additional pipe? Why 6-inch? Why only 4-inch is also possible? So we're going through these topics, and now we're going to share to the next screen where you will see the PowerPoint, and I'm switching to my desk computer. So see you in a few seconds. Thank you. Okay, I think the presentation is on the screen. Going to switch to presentation mode. So as mentioned, the topic of the day is designing drainage without compromise, DIN EN 12056, which is the European standard, what we also will see just afterwards. So the agenda after this introduction is quickly about of the Geberit as a company, why we do this kind of modules, who we are, very brief. Then we go through the history of drainage, where all started. It's quite short. Then the basics of drainage systems. I was talking about the air circulation. This is a point. Then about material and characteristics. Obviously, the material is an important part of the drainage system. Then there are different system types. We have seen 2 types on this module, and then how to plan a system in 5 steps. That's just a rough guide. And then Geberit super tube. That's basically what we have seen as well. Why we can, or what is behind super tube, and then we are already at the summary. So Geberit.
Sorry to interject. Remo, could you put your camera on as well? We can't see you at the moment.
Of course. Can do that. So
yes, perfect. Thank you.
Again. Okay, presentation is good on the screen. Fine. All right. Presentation mode. Yeah, sorry for that. So back on track. Sorry for that. So yeah, Geberit, who we are. We are listed in the 6 Swiss exchange stock markets since 2012, including the Swiss Market Index. So one of the leading companies in Switzerland and the European market leader in sanitary products. We have a global presence with around 12,000 employees in total, spread over 50 countries with our proper setups, and we have 29 production sites, which are mainly very closely to our key markets. We have 3 brands here which are known in the Middle East, which is obviously, of course, Geberit, but also Colo and Twyford can be found. Our successful business model is the push and pull principle. So we have a lot of technical advisors and consultants out in the market to really, next to the products, offer a really good service to our stakeholders. The company's history. So in 1874, Geberit has been founded by a gentleman called Caspar Melchior Gebert in a tiny in a small village close to Zurich at the nice lake of Zurich at the southern end. And he was basically, or his first invention was in 1905 the Phoenix. That was the name of this product, the very first wooden cistern. In the 50s, then Geberit, and also where comes the, you can see from Gebert there is an I in the name, from Gebert to Geberit. This comes because of the famous material plastic of bakelite. So then everything from wood and these other materials, Geberit started to work with the plastics as raw materials, and since today, of course, that dominates our products. So in the 50s, the first plastic cistern. Then also, I mean, what we're talking today, we have a rich history when it comes to drainage systems in the 50s. And then I think that was a major milestone in the history of Geberit in 1964, where the flush technology went into the wall, concealed. And I think this is really also one of the synonyms what Geberit stands for. It's the actuator plates and the concealed cisterns as one of our key products, and that is not different here in the Middle East. And then some other products came up, so installation system, shower toilets. Also, when we think about water supply, how comes the water into the building? How is it distributed? There we have some systems and solutions. And in 2004, this was an acquisition in Germany, Geberit Mapress. So that is the supply system for all different kind of media, from gases, water, whatsoever, different pressures for the industry. Not only, also for hot and cold water, based on stainless steel or different type of steels. In 2010, then there was a Geberit Monolith, a very nice product for renovation business. So it's not a conceal, it's a cistern in a very nice look and with nice functions. And 2015, then that was quite a strategic move when Geberit did another acquisition, and since 7 years now, we are also present much stronger in front of the wall. So in Geberit, we're talking that we are coming from inside the wall, behind the wall, as we have seen in the 60s when the cistern went into it, and all the pipe work and everything, which is usually behind the wall. So we are very much famous for the know-how installed inside the wall, but we made a step outside the wall, and now we have all ranges and segments of bathroom products, not only ceramics, showers, bathtubs, mirrors, furniture, and so on and so forth. This is a little bit about the history. So today we have 3 product areas, which is the installation flushing systems, the bathroom systems, and the drainage and supply systems. A key pillar of the strategy is, of course, innovation and technology. Without innovation technology, it is very difficult, of course, in the market environment. So usually like around 2.5% of the annual net sales. I think I didn't mention our size of company. We have around $2 billion turnover achieved last year. So 2.5% of this of net sales is invested into into technology and research and development. And today we are talking about hydraulics and virtual engineering, or the SuperTube, or our know-how is coming on of course a long-lasting history in these two fields. But not only hydraulics and virtual engineering, we also look into acoustics, fire protection, electronics, material science, statics, process engineering when we think about production process in the value chain, or also surface technology. To sum up, with Geberit, we can manage the water flow within the entire building. So when the water comes into the building, it's distributed, and then we think on the user. What are the needs there? Good function with a good design in the bathroom or in the wet areas, and then we also think about how to get rid of the waste and soil water, or how to collect and drain rainwater. So we're not only focusing on good products, we really try to focus on the complete solution, like for example the hydraulically optimized drainage system, which will save space or time during installation. Or if you think about, that's a classic example, the matched balance of flush performance between a concealed cistern and a wall-hung WC. And there are many other examples where there are synergies if we see the building as a system. Enough about our company. Now let's go into the topic of this CPD. So the history of drainage. I mean, how all started from very rudimental to nowadays luxury and modern living, and flushing a toilet without noticing where the water is coming from and where it is going to. What was always, of course, an issue with the drainage system was the bad smell. So if we think when it was integrated then into the building, then we see here it's an open system. So of course this would have caused a very bad smell, and also in terms of hygiene and comfort, this was definitely not a good solution. Then to prevent the bad smell, what we can see here, a water seal or the water seal basically has been added to the devices. So basically the gases could not exit the drainage pipe system. So that was then coming, and then later on, in terms of hydraulics, there was a ventilation added, because also here a closed system then from a hydraulic perspective will cause problems. We will see that later on. So an open system has been created, and also the waste and soil has been collected. And then finally also there were sewage systems added. I mean, if we think back to the Great Stink, which was an event in central London in July and August in 1858, during which the hot weather really exacerbated the smell of untreated human waste and industrial effluents that was present on the banks of the River Thames. So the river was just like simply the sewage canal. So then, of course, the key is to have an entire system, a pipe system with a sewage system, and then the wastewater treatment as well. We are focusing on the building, let's say the building perimeter inside the building of the system. So we're going to focus here on how this should be treated here inside the building. So what are the basics of a drainage system? Definitely we need to see what are the requirements. I mean, that is first of all hydraulics. It shouldn't create any blockages. It shouldn't be self-siphonic. So that means if you can hear, for example, you're draining your bathtub after a bath, and you can hear your floor drain cover making some noise, or you hear that gurgling noise. So that means your drainage system is crying for some air and trying to get air into the system. It will suck air into the system. So that means there's an issue with the hydraulics of the system. Definitely there should be no bad smell escaping. into the building. Therefore, as seen, we have this depth of water seal which should be stable, and this means it will remain stable if there is no significant overpressure or negative pressure will suck the water into the system, or as mentioned in the introduction, that water will, in the worst case, come out, spit out of a WC, for example. So that is key, of course, and also water will evaporate. That is another issue which is not related to the pipe system itself. That has more to do with the environment and the air condition within the building. Then the system needs to be corrosion resistant. This has to do with the material. It needs to be temperature resistant. If we're thinking about kitchen, industrial kitchens, for example, but also within the household, so temperatures up to 80 degrees Celsius, or in short term even up to 100 degrees Celsius can occur. Then it needs to have a good mechanical strength, so a system needs to be durable in terms of material as well. There we go, high durability. Sometimes, or even more, of course, low sound influence is something, depending on the building type, and as well on the different room type. We have different requirements in terms of acoustics. So it starts with the design. Where do I place my bathroom? Where do I place my shafts, the pipe work, pipe routing? Already in the design stage, acoustics becomes a topic, not only the material, the good acoustic material itself. It should be easy and safe to install. I think that is clear. So all the drainage system, no matter what standard is behind, or what material or brand, manufacturer whatsoever, the main requirement of the drainage system is that waste and soil water, solids and liquids, should be carried away quickly, quietly, without blockage, and without the escape of foul air into the building. That is a quote from Mr. Clark, which really nicely summarizes the requirements. So now, if we look into the elements within the drainage system, then pretty simple. We have three elements, which is air, dirt particles, and water. So we see it here, a sectional view through a pipe, and also a side view. The air needs to have its spacer for circulation, next, of course, to a good and sufficient flow. So the most important here of these three, for a proper function of the system, is the air. And just to imagine, for 1,000 liters of water, we require the amount about 20 to 35 times more of air to the system properly work. So we're talking about the filling ratio between the ratio of the height of the water and the inner diameter of the pipe. And ideally, this should be between 0.5 to 0.8. So that means we always have this kind of scenario where we have this right balance between air and water. That is the most important in designing a drainage system. If on the other hand, this would be below, so this ratio of water height and inner diameter is below 0.5, you can imagine insufficient flow will be a result. Of course, the slope will play as well an important role. There are some guidelines, minimum and maximum percentage per meter for the slope. But it is clear if there's too less of water in a too big pipe, then it will not flow sufficiently and can cause issues. On the other way around, if this filling ratio is too high, it's above the 0.8, then there is no space for the air. It cannot circulate, and it will be what I mentioned with the bathtub example. It will cause a siphonic effect, which means a siphonic effect. The pipe will fill fully with water, and therefore a negative pressure will occur within the pipe and it will suck away the water, but in the same time this negative pressure which will occur in the pipe will also empty the water seal we're having in the traps, and then afterwards the bad smell will go into the building. So the appropriate size and gradient of the discharge pipe is the key, and therefore we have standards which define how much water should be drained in which size of pipe, and of course it depends what fixture we are having, WC, wash basin, shower, and so on and so forth. Another theory which is interesting or important to know is the air circulation and the water flow in vertical pipes, in all the shafts, in the ducts, in the downpipe. So we see that, and we have seen that in the module, the water is always around the pipe and circulating, and the air circulation happens in the center of the pipe. So this is how it looks. So now here the speed and the velocity of the water is also an important factor. So theoretically, it's a little bit physics. I mean, we see here that the formula of the speed, and we draw that curve here on this chart where we see here on the vertical axis the speed in meter per second, and on the horizontal axis we see the height of the pipe in meters. So theoretically, the speed would increase by height, because you see the only variable here is the h. 2 is fixed, g is our is a constant, and the height is variable. So this will go, the greater h, the higher the speed. But of course, and this is what we want to achieve. Number 3, in a partial filled situation, in a real situation, we will have air, and we will have also a resistance of the air column within the pipe. We have friction of the pipe material and so on. So here in a practical situation, we know from research that after around 35 meters, the maximum velocity of 13 meters per second is reached. Moving forward, when we talk about material and its characteristics, we mentioned it should be of high durability and corrosion resistant, easy to install, safe, and so on and so forth. So high density polyethylene is the main material what Geberit thinks is suiting here the best. It's resistant against corrosion, very impact resistant against chemicals, temperatures, the range I mentioned, and also UV resistant. It can be welded, so it's a welding process to do the connections, either with an electrofusion sleeve or with the welding tool. So it's a permanent seal, that means welding. It's a very strong connection. And there are all, of course, you need to have in your system also all different components then to put together your drainage system. And at the end of the day, we always say good engineering is simple and is reducing complexity. And this is something definitely we always want to carry forward. The jointing techniques which exist are, as mentioned, a butt welding. So that's just a fusion welding. The electrofusion, coupling, but also non-tension or non-tensile connections are there, such as the ring seal sockets or expansion sockets. We also need to consider the thermal expansion of the materials. That is for all the materials. And there's some in some special applications, sometimes you need a screw threaded joint or even a flange connection if we need to pump wastewater from a basement level to street level, for example. Then we need to have sometimes a flange connection, for example. But the most important is to have really strong and reliable connections. You know, the pipe system will be installed behind the wall, behind walls, and once it is installed, we don't really want to access anymore. We want to have peace of mind. Yeah, to summarize, the high density polyethylene or HDP, it's easy to handle, very simple, strong and reliable joints. That is important for a system. So now if we are looking into the different drainage system types, we differentiate a little bit between European layouts and GCC layouts. So what we're seeing here in the region, to create a little bit of course, the proximity here to the region. We see on top the European influence, which is usually coming with whenever possible with the single stack. So one pipe, meaning the waste and soil water is drained away in the same pipe. And then we look into the horizontal branch connections. And here we see a difference, that this can be either below the bathroom, so cross floor, or cast into the concrete. In Switzerland, for example, this is the common practice. So the pipe work is prefabricated, all welded together, and then powered into the concrete. That, of course, requires a very good planning. Or we have a single stack system on the same floor. So that means we try to keep all the connections within the bathroom. This has some advantages if you think about the penetration of the civil engineering, of the concrete, about the ceiling, but also the acoustics. I mean, here we are transferring, for example, the noise into the neighbors or into the floor below. So if we can keep it within the same bathroom, that will give us some advantages in terms of acoustics, but also in terms of fire protections, for example. And if you see the British American influenced systems, which we see here in the region, the triple stack mainly in UAE. So here we are separating waste and soil, and if required, or most often, we have a center line which is for the ventilation. So we have 3 pipe system plus ventilation. So meaning ending up then in 3 pipes. And as well, of course, then we see the separation of the branch pipes, so the waste and soil separated. And classical, of course, they require very strong requirement of a floor drain. And here then the bathtub or the other fixtures basically are drained over the floor drain and then connect to the respective stack. And all happens cross floor, mainly due to the floor drain. Then more in Saudi Arabia, we see more the dual stack system, or also in Abu Dhabi, we come across dual stack systems. Still, waste and soil is separated, but only waste soil. But this has to do then also with how much water you want to drain, what is the capacity required, if you need this ventilation or not. As well, cross floor with the floor drain. Or what is another solution would be a single stack system with the same layout or principles when it comes to the floor connections. So what is our philosophy within Geberit? It's a simplification, but without compromise. And without compromise meaning all the requirements mentioned in the beginning, that is no discussion, that needs to be given, but simplification in terms of complexity, which will give us benefits in terms of space saving, in terms of planning efforts, coordination, but also installation and load to the structure and so on and so forth. So there is a solution or there is the choice between having a triple stack system or a single stack system with achieving the same. If we look then from a standard perspective, we mentioned, I mean, the title of the CPD is Designing Drainage Without Compromise, EN or EN 12056. So we see that the EN 12056, also mentioned in the introduction, is defining the building drainage inside the building. And then the basically plot or the sewage drainage, rainwater or sewage is then defined in another EN standard. So it's important to know that this standard is responsible, let's say, for within the building. And then when we look into the standard, it consists of 5 different parts, a general part, and then what we are talking about today is part number 2, the sanitary pipework layout and calculation. So really here within this part, there are the tables for the dimensioning and all the regulations required for calculating a system here in the region. Part 3 is about roof drainage, and part 4 is for lifting plants. And then the last part is about the testing, maintenance, system in use, and so on and so forth. Then this is when we look now into the second part of the standard. Then the key in this or in the introduction of the second part, the standard talks about 4 different systems, and again we put here in brackets some background. System 1, where it's mainly in use or where it's coming from. It's made from Central Europe, Germany, Switzerland, and Austria. So the system 1 is based, when we think about here the filling ratio, that is really based on this filling ratio 0.5 to 0.8. So the dimensioning is then a single stack system with partially filled branch discharge pipes. Sanitary appliances are connected to partly filled branch discharge pipe, are designed with a filling degree of 0.5 and are connected to a single discharge stack. That is the basis of system 1. Then there is system 2, that's more than the Scandinavian practice in Northern Europe, where they allow a filling degree up to 70%. Then there is system 3, which historically was the UK practice, and here the filling ratio would be allowed to 1.0. So what would it mean? Then let me think, okay, what happens? This negative pressure, where is the air coming from? This would mean if we then would look, or we would design according to that system, then this requires a lot of ventilation pipes. So then we talk about the fully vented system. With every discharge unit needs to have a separate ventilation pipe to provide the air from another pipe, which makes it, in our perspective, then very complex, a lot of pipes, and so on. System 4 is the French practice, and this is a mix between 1, 2, and 3. And we are focusing on system 1, which is the 0.5 filling ratio. So everything we're talking about is based on this system. Now, how to plan a system in 5 steps. What is required, first of all, and what does a consultant need to have? Of course, the necessary basic information about the project, which is floor plan, the layout, the building type, and we need to see a first schematic sketch to see what is all connected to which stack. Of course, it has to do with the positioning of the ducts, and the building type is required because of the frequency factor. So if you think a residential building, a multi-story residential building has a different, or the users will show a different pattern of usage than a hotel or an airport or a museum, for example. So there are different patterns of the usage of the toilets, which will give us a different frequency factor we will consider then for the calculation. So after having all the basic information about the project, the architectural design, and having an overview in a schematic view, then from there we already can go into the simple mathematical calculation. And here we are using design units. So every fixture has a design unit, which is one design unit is representing 1 liter per second. So then a wash basin, for example, has a 0.5 liters per second. A shower is calculated with 0.8 liters per second, and a WC according to nowadays, of course, we differentiate as well already here. If we have a 6 and 3 liter flushing system, a 4 and 2 liter system for a LEED project, for example, this also will have an impact on the drainage system, which we design. And this starts with the design unit of the fixture, which is defined by the standard. So we are going to allocate all the design units in the building. We know the frequency factor from the type of building, which we will see right afterwards how this is categorized. And then we create the sum of the design units. So we calculate together all the design units from the top floor to the basement for one stack. And we put it in this empiric formula, which will give us the Q max, which is the maximum flow rate in liters per second. And here is an example. So for a residential building, which will have a frequency factor of 0.5, we want to drain 576 design units. This will result in 12 liters per second. So now when I know I need to drain 12 liters per second in one stack, then I can go to the to choose the right system with the right performance. Before we do that, we quickly look into the frequency factor as promised. So here, this is the table from the standard, and it's pretty simple, straightforward. We have 0.5 for an irregular use. So that means a residential building or guest houses or offices. A regular use, which is then 0.7. That is for hospitals, schools, restaurants, and hotels. And we have 1.0 for public toilets or shower rooms. I mean, in sport facilities, for example, there we have 1.0. It can be that also we have some special use in laboratories that maybe in a short time it can be, it requires more. So we can add a safety factor there of, for example, 1.2. Basically, this is a decision of the engineer what factor suits best of the building type. So now we're going to choose the right drainage system according to the standard, and here we can choose, and we have a variety of systems. A single stack system. We can choose a parallel vented system direct. So this is what we have seen also on the module. This means we have a pipe to drain the waste and soil, plus we are having an added parallel ventilation. There is also the parallel vented system called indirect. So indirect means there's an indirect ventilation. This depends on the layout, on the architectural layout, how are the fixtures arranged. It's less common to use that one, but it exists. And then we have some special solutions from manufacturers. In our case, it's the Geberit Solvent or Geberit Super Tube system with a special fitting, what we have seen on the module. And then we have this solution. So what are the differences? Now you would probably ask, what are the differences? And it's of course the performance, and we calculated in our example 12 liters. So we see again here an overview. And I'm going to explain quickly the chart. So we see the capacity of the system here in liters per second from 0 to 18. And then we have three colors from left to right is always the dimension of the stack downpipe from 110 to 125 and to 160. And then you see the different colors and indicated how much the capacity is of that system. And a main impact has the type of connection of the branches. What I have shown you on our module was the solvent fitting, this special fitting, and this fitting allows to keep the stack on 110. So you see with this fitting and a 110 stack, I have 12 liters. If I'm going to use this branch connection, which is called swept entry, so it's hydraulically a little bit optimized thanks to this radius you can see here. The maximum capacity is 5.2. If I use a ball fitting or an ordinary 88.5 degree branch fitting with the sharp angle, then I only can drain 4 liters with a 110 pipe. So traditionally what happens, then I have to increase the diameter, or I have to add a ventilation, and this is what we see here. We see always single stack and parallel vented. So if I'm going to increase the diameter of the downpipe, you can imagine I can drain more water and more there is more space for the air to circulate. And then if I'm going to add and attach that second ventilation, then more air can circulate and more water again I can drain. This is simply what we see here on this visualization, and therefore traditionally here in the region we see that parallel vented system, because we have high buildings which exceed quite quickly 4 or 5 liters, 5.2 liters. So then I need to choose the system, and then commonly it goes into a 160 with the parallel ventilation. What we see here, 12.4. Unfortunately, what we see here is 12.4 with the swept entry doesn't exist. So there is no fittings of swept entry with 160. But there is a solvent fitting for a 110. So see, there is then the choice basically to choose the appropriate system for the capacity. Maybe to give you an idea what it means for 5.2 liters, I would say a standard building with, let's say, a normal bathroom layout, meaning a shower or a bathtub, floor drain, wash basin, WC. That's roughly like 4 DUs, design units per floor, and then 6 to 7 floors, let's say. Then we will be roughly reaching the limit of the 110 single stack. And as of, again, depending on the layout, or is it the back-to-back like in a hotel, do I drain two bathrooms in one stack, then it will increase the number of fixtures on my floor, so it will, you see, multiply that, again, depending. But roughly you can imagine like G+7, G+8 is somehow where there is this break even then to where people or consultants choose to increase the diameter and add the parallel ventilation. But if you do it like from the beginning, you really go into each design and you design entirely your whole system and can choose. We see that basically very similar here in that table. It's exactly the same message than before. But if we go back to the example from the beginning with these 12 liters, then we see here the same overview, which is now here it's the layout, how it is shown in the standard. Then we see that I can choose, you see the maximum load in liters, I can choose this one here, which is a 160 stack system with a swept entry. But as mentioned, I have not yet seen this kind of fitting on the market, so it's not an option. Then I can choose here 12.4. Again, it's higher than what I require. I can choose a 160 parallel vented with the 90 millimeter secondary ventilation. So that is something I could consider. I could consider also this one here, which has a maximum of 16.1. That's the 160/90 with, again, swept entry and parallel ventilation. But again, I don't find this product here on the market, so it's not an option. Then I can go to this Geberit solvent subtube solution, which has a maximum of 12 liters, and I can keep a single stack with 110, or well, it's not necessary. The 17 maximum would be the solvent system with diameter of 160, but if I can do it with 110, then of course I will choose the more simple solution. So I will end up in having two options on the table, either the parallel vented, and then here in the region it would be the triple stack, because I wanna separate waste and salt. This is not a hydraulic requirement. You see, I could easily drain 12.4, which is 160 plus the 90, or just a 110. So both will work according to standard. I mean, that is with a lot of history and testing and knowledge, empirical knowledge here in these tables. So that works. So if I have, then step 3 was dimensioning or choosing the right system. So when I define my system, my stacks, I know, okay, I want to go with a single stack 110 with subtube, for example. Then I need to calculate my branches horizontally. And here we have 2 different types, which is also quite straightforward. We have single branch pipes, meaning the pipe here is draining just one fixture, like here it's the shower, and here is it's the wash basin. Or we have collector branch pipes, which are draining more than one fixture. As mentioned, we have the design unit. So here we have this overview and the drainage fixture. Then it's defined the design unit. And here we see, for example, the difference between the 4 and 4.5 liter concealed cistern or flush tank with 1.8 DUs, and nowadays the standard 6 and 3, or basically in Saudi Arabia the standard is 4.5 and 3 liters because of SASO requirements, and here in the UAE ESMA 4-star would be 6 and 3 liters, and ESMA 5-star water efficiency label 5-star rating would be the 4.5, 3. For the lead, we could even go further for 4 and 2 liters. So obviously, the point here is the discharge unit has a little bit an influence. And if you think on a large scale building, then the 0.2 can sometimes make or will make a difference also on the designing of your drainage system. I think 7.5 liters and 9 liters, that shouldn't be considered anymore. That's too much. It's not required to flush properly a WC. But coming back to the branch pipes, this is what we wanna elaborate here. We have these design units, and we differ between unventilated and ventilated branch pipes. So also there is some limitation. If I go back here, we see we talk about the ventilation of the branch pipe, this means just the horizontal branch here is not ventilated. So after certain distance, which is 4 meters, or certain complexity, number of changes of direction, also the air will not reach from, the air will come from the stack and will need to pass here to the furthest fixture. Then we have to add also a ventilation back to the stack. But that's all, I think, already too much of details. So this is basically how we then design the branch pipes according to these tables, and there are I define then the size. You see there is a guidance here on the size of my branch or collector branch then. Furthermore, then the fifth step, so we have done the stack, we have looked at the bathrooms on the horizontal connection. So now we need to design the collector pipe. So on the podium level, all the stacks are coming down, put them in one pipe or in two, depending on different aspects, safety, hydraulics again, maximum allowed diameters by municipality, and so on. So here we have also quite straightforward, two tables split into again filling ratio. So here 50% filling ratio, and you see it's then according to the slope. So we see here is the slope we are giving for the horizontal collector line, and here the diameter, and inside we find the maximum flow rate. So if I'm going to search for my 12 liters, and traditionally we are talking about 1 to 1.5% max. So let's say 1%, 50% ratio. Here maximum 14.2 would require a 200 millimeter horizontal collector. So if I'm ending my stack system, going into collector outside, I already require a 200. And then if I'm collecting several stacks together, again, I will calculate with simultaneously. Not every stack will come simultaneously. So then calculate this value again, go into this table. The second table here is with 70% filling ratio. So we'll allow a bit more water in the same diameter compared to the 50%. Usually a rule of thumb, what the consultant would tell you is that the 50% he's using inside the building, so he's adding a little bit that kind of safety factor, and outside the building towards the sewage or to the manhole, then we're going to 70%. Let's say that's but the decision of the consultant, or also some requirements by municipality, what filling ratio should be used here. I think that's quite in a very short time giving you a brief overview on how to dimension properly a drainage system. So you start with the layout, with the design. You have your formula to calculate your total liters per second. You go and choose your system. Then you look at the branch pipes and the layout again, how this is dimensioned. You bring everything down, then you look at your collectors, how big, how many, and then outside to the building. So that's roughly how you go through the dimensioning. So now last topic, then we are already through here. The content is coming back to our module and Geberit SuperTube. And here, yeah, we start with the space as a precious good, and how can you save space with the hydraulic construction and save even time during installation and so on. So I'm going to show you a nice quick video about Geberit SuperTube, and now again I realize I didn't share with. No, I think it is shared with sound. Else, please interrupt if there is no sound coming. We're going to see a quick video, which is really nice now, summarizing a little bit what we were talking about, and is giving you a better idea about Geberit SuperTube. So here we go.
Living spaces and commercial spaces are in short supply, and they are expensive. They have to be flexible and adaptable in terms of both use and design. Solutions that minimize the space required for facilities like a hydraulically optimized drainage system would be most welcome. The problem: conventional drainage systems take up valuable space with their large pipe diameters and ventilation pipes running in parallel. In addition, horizontal pipelines, offset, or in the collector pipe, for example, have to be installed with a slope. Geberit SuperTube solves these problems. This flow-optimized system with its sophisticated fittings can be relied upon for a continuous column of air in the discharge pipe. There is no need for an additional ventilation pipe. The diameter of the pipelines can be reduced to D110, and horizontal pipelines up to 6 meters long do not require a slope. This equates to a space saving of up to 20% in the vertical duct. The gain in room height equates to up to 40% less suspension distance being required. More space with no loss of performance. With Geberit SuperTube, the maximum discharge capacity is 12 liters per second. Geberit SuperTube consists of the Geberit PE Sovent fitting, Geberit PE bottom turn bend, and Geberit PE backflip bend. Geberit Sovent sets outflowing water in rotation and guides it around the floor connection. Inflowing water can flow in without a hydraulic blockage being created. The air column in the stack is maintained. In the case of a change in direction, for an offset, for example, a bottom turn bend is built in. The annular flow becomes a layered flow without disrupting the column of air. This change significantly reduces impulse losses compared with conventional bends. As a result, there is no need for the pipes to be installed with slopes. At the end of the offset, the Geberit backflip bend sets the water in rotation again. The air column is maintained. This is how optimized hydraulics can create more living space. Geberit SuperTube offers yet another benefit: simpler planning of the system and even faster installation. And that's where Geberit comes in. Take advantage of Geberit's personal project service for planning, implementation, or directly at the building site. Geberit SuperTube, the space gaining system.
All right, I think that video summarized quite well. I mean, the basics of the hydraulic system. We have seen the fitting, which has that huge impact on the system. How inflowing water is causing troubles or not in terms of hydraulics. And I think this should give you now, after the session, a good summary. So the solution, I mean, is definitely for space saving, but not only. Of course, we have seen that the conventional system is with usually 160 with this 90 ventilation pipe, and the horizontal pipes is another topic we're adding here now. It requires the slope, and there is a solution with loads of engineering and research behind, where you can make it basically more simple. So why not using a more simple solution without any compromise behind it? So basically you can achieve exactly the same, which is less complexity, and on top of that, save space within the building and install less material here. Yeah, these three special fittings made it possible. So it's all about finding the good hydraulics and ensuring really that continuous air column in the stacks. So here it includes Sovent fitting, bottom turn bend, and then a backflip bend. These three special fitting enable this circulation of the air with a maximum flow capacity of 12 liters per second in only a 110 single stack system. So to summarize, the SuperTube technology, it offers a simple, space-saving and truly innovative solution for drainage systems in high-rise buildings from the top floor to the basement. So some benefits, of course, I mentioned space-saving, increase of net floor area, increase of room height in certain cases, time saving in the planning and coordination process, and also when it comes to construction, it will give a faster installation because of smaller pipes and no ventilation to install. I'm seeing time-wise, I'm exaggerating a little bit. We're coming to the summary. I hope everybody's still with us, although I'm a bit over the time as promised. But so to summarize, I mean, safe drainage is really not mere coincidence. It's about good materials. It needs to have a clear standard, which is implemented and followed. There is many years of experience in hydraulics and flow technology in the various markets, and then various firms. So it's not a coincidence, really. It's about engineering and engineered solutions with a lot of experience in hydraulics, and also nowadays, of course, fluid simulation. And we see here on the other side laboratory and engineer specialists, which are researching and always trying to bring new innovation, new technology to make life more easy. So on that note, we could go over to the Q&A session. That was the content of the CPD, Design and Grade Without Compromise. So please, Mituna, back to you.
Thank you, Remo, for that wonderful presentation as always. Let's move to the Q&A session. So, please submit any questions regarding today's presentation in the Q&A bar on the right if you haven't already, and we can just go through them. I know we already have a couple of questions that have come in, Remo, so let's begin there. So, Remo, Amina asks, how do you design your products and projects according to sustainability standards in architecture and in regards to climate change?
Yeah, well, first of all, there is good question. Well, the material itself can have an impact here. What is the raw material? And I mean, in these kind of questions, usually you look at the whole value chain of the product. And then in LEED, for example, there is this process to see how much is recycled material in a product, where is it coming from, how is it shipped around to the place. So this question looks at the whole value chain here. I mean, with HDP, it's a recyclable material. It's environmental friendly. And SuperTube, I mean, you could also then argue that it reduces the amount of material used, so you can cut down the total volume of material. So then you could conclude here, okay, you need to ship less material, logistics, and so on. So it's a very broad question. That's I would
Perfect,
like that.
Mohammed asks if you have any references for the formulas. Does Geberit have a link perhaps we could share with candidates here?
Reference formulas. We have reference projects with this kind of system. Yes, in the region. Yes, we do have. We do have municipality approval in Dubai for this kind of system as well. I mean, we have loads of information available online on our website, international.geberit.com. We have a YouTube channel. We have different tools and so on. To be very specific, probably get in touch with us so we can then prepare the right package of information here to provide.
Perfect, thank you. And Robert asks, how does the SuperTube bottom turn vent work? Where is the foul air vented to?
Yeah, so the bottom turn vent engineered in that way that we have seen the circular or the annular flow was converted into the layered flow. So it's just by the shape of the fitting so that the water is changed in its flow, and there is enough space for the air to circulate. So we are not creating negative pressure or overpressure. So it's just the fitting, the geometry and the engineering of the fitting itself, which makes it possible.
Mm-hmm.
So the air remains within that pen. Basically, it can circulate there.
Great. And Jasbir asks, are there any other alternatives in the market for HDPE, particularly for drainage of chemicals from laboratories?
Yeah, of course, it's a market. There is next to Geberit, there is different manufacturers offering HDP as well. Yes.
Great. A candidate would like to know of any events you have encountered where the architecture of the building has caused difficulties in designing of the drainage. It's quite a specific question.
So the question is for a specific project where there was a challenge, correct?
Mm-hmm. So if you can see the question that's come from Catherine, she said, I would like to know of any events you have encountered where the architecture of the building has caused difficulties in design.
Yeah, well, that every project has its own characteristics, as you know. So there will be here there are always some challenges, or I mean that is about in designing buildings. That's I think also the interesting part of it, that you have to find some special solutions here and there. Yeah, we have some. If you look into our references, sometimes the shape of the commercial bank in Mauritius is a good example where we did the roof. Could design the roof drainage. It's a very it's a round building, so it doesn't have a clear roof area, so that was quite special. Or I mean, all buildings usually are the where you have a large span, or not a lot of space to position your, where you don't have a lot of ducts, for example, or where they are not straight above each other. So you will face different challenges here and there, and I think this is what you observe in your meetings, project meetings with MEP consultants, and how to solve different challenges.
Absolutely. Sandra says, thank you, Remo, clear and informative as always. Are you able to advise if the super tube system has been installed much in the GCC? Are there examples of it in use, and can it be used in complex buildings such as hospitals?
Yeah, it's under construction in 3 projects. That's in MBR City Master Development, Schober Heartland. So there are three projects ongoing. One is 70-80% completion stage now. So the system is installed. So now they're finishing the project. It will go operational this year. Then there are 2 other projects in construction. I mean, the system is pretty new. 2019 we came up with it. So now it's 3 projects. We're working on some other projects. I mean, if you have projects where you this is always what we offer. I mean, we have this very decent project service. We look into projects, look at the layout and propose a typical layout. Do all. I mean, basically this calculation, what we have shown, we do that as a proposal, then to show the direct and indirect benefits for the particular project. This varies always from, depending on what mentioned, complexity or type of project. So then, we work there with the different stakeholders involved and try to show these benefits with of course the cost as well, which is a very important, or if not one of the most important factors. So we do that. We offer that service, to see what would be the impact of having the, let's say, traditional system versus something new, a new innovation, and then there usually then the discussion or decision starts or also ends. So just approach us, and we're more than happy to look into a project. Yeah.
Perfect. Thank you, Remo. Perhaps the last question for today, and a general one. Someone has asked, what is the impact of COVID-19 on the drainage and sanitation sector, and how does restroom design change during this time? So quite a broad question, Remo.
Yeah. It's interesting. There is, of course, then there is some nice articles online in LinkedIn, and we have a very Mr. Ashwin Chitun. I could mention here. He's an engineer here in in the region, and he posted just recently on LinkedIn his paper about this topic. So the spread of germs in drainage systems. So there is some people specifically thinking about that topic, and we're looking into that as well. I mean, hygiene, of course, is very important when it comes to the bathroom, within the drainage system as well. Yeah, so yeah, we could have a CPD about this topic, but let's search for his name's Ashwin Chetan, and he was also an engineer of the year, and he's this year also again is nominated from MEP and the MEP award. So check in LinkedIn, and there you will find some I think that's the most recent papers you can find about the topic.
Perfect, thank you, Remo. I don't see any further questions that have come in actually, so I think we can perhaps close today's session if there's nothing else. Yeah, I don't see anything else coming in. So thank you, Remo, for answering all those questions.
Yeah, thank you.
Absolutely, and thank you, Luis and Geberit, for your kind support in the series as always. So we will be closing today's session. Once again, may I remind you all, we will be hosting the second module of the RIBA Gulf live lunch talks tomorrow on urban greenways for Dubai. And day after, we will be hosting the Ways Ahead session with Alan Jones. So please click on the registration link in the chat bar to get your tickets. And thank you everyone for joining us today. It's been a great session.